Welcome everybody. In this video we are going to discuss the DCS Stennis model and the IFLOLS as presented in game. Basically we're going to talk about how it's wrong and what that effectively means to the simmer here. So one of the first things, if it's wrong, what does right look like? Well, we can use a few things. We can determine what right looks like from available data. The LSO NATOPS and the deck layout will get you what you need to figure out all sorts of geometry, including the effective focal point of the lens system. That's the improved Fresnel optical lens system. All right, so the starting point of data here is basically mathematically based on two things. I'm going to use two. The entire premise of landing on a carrier is based on aligning the hook with the wires while maintaining safe clearance between the hook, the lowest dangly bit on the plane, and the ramp, the first point on the boat you'll likely encounter. This is done to keep the descent rate of the plane within its designed operational limits, as well as provide a reasonably similar landing envelope for all carrier-based aircraft. It's a bit of an oversimplification to say, but all carrier-based planes fly the same geometry. For our starting point, we'll use the hook touchdown point distance from the ramp and the basic angle provided in the LSO NATOPS and the ARB 6312E, that's Airmen Recovery Bulletin. We'll end up deriving and confirming the hook to ramp clearance. So using basic Trig, we can calculate the hook to ramp clearance. We see that it is in agreement with the published value in ARB 6312E. So when you round up 14.063 to 14.1, that's about 3/4 of an inch off. So it's negligible. Rounding up makes sense, especially for purposes of safety. Right. Now we want to see where a 230-foot hook touchdown point puts us relative to the wires. Rounding again for everyday calculation, who cares about 1.8 inches in this context, we can see that this puts us in the middle of the 2 and 3 wire. This seems like a logical spot to aim for, as you have the same amount of real estate forward and aft of that point to catch a wire. 2 forward and 2 behind, right? So, correcting, or the corresponding eye path here. Figure 2 from ARB 10-10F shows this best, although it's a little cluttered with extra data. And you should note that there is an error in the illustration, and that the hook should be depicted deployed, and the illustration dimensions be repositioned accordingly, but we get the point here. Since the inertial reference frame is the moving boat, this is why you can't fly a glide slope using your HUD ladder. Inertial reference frame is like someone tossing a ball up and down in a car moving at constant speed. To the occupant of the car, the ball moves up and down, but to an outside observer, the ball follows a parabolic path. The boat is still moving as soon as you aim your total velocity vector at the boat and attempt to hold that 3.5-degree glide slope, you will end up in a one-wire or worse. So fly the ball and only the ball. The more astute may have realized that you are flying a descending glide slope trend relative to your jet, and it only matches the 3.5-degree basic angle of the boat at touchdown. At the beginning of the groove, it's about 2.9 degrees and steepens to 3.5 at touchdown. Technically, this alters the hook eye value a little bit, but it's so negligible. The IFLOLS system can be adjusted to project the light uniquely to each aircraft type and configuration, such that each respective aircraft will strike its hook at the desired point, if the pilot does their job perfectly, that is. So, for an on-speed Hornet, the optical touchdown point is 497 feet forward of the ramp, along the center line of the angled deck. So, since the IFLOLS sits left of the runway by 86 feet or so, we know that it corrects the projected light to be valid at the center line of the angled deck. We can think of the IFLOLS lights as emitting along the angled deck because they effectively are, because of the optics and mechanics of the IFLOLS itself. This is another reason to stay on center line in the groove, as the meatball is only valid along the center line, with increasing error the further you deviate from the center line of that angled deck. Since we know the optical touchdown point and the basic angle, we can calculate the height off the deck the basic angle emits from at the projected IFLOLS. We get a slightly different number than Table 1 of ARB 6312E since we assume a flat deck. In reality, there is about 4 inches of flight deck camber, so it's a saddle shape, so it drains water. We're only off about 5/8 of an inch, likely due to omitting the deck camber and or perhaps a unstated assumption of the literal IFLOLS position rather than the effective one above the center line of the angled deck. So it's negligible for our analysis. Note the asterisk statement indicates the existence of a middle cell in the IFLOLS. There is no middle cell, as there are 12 total, 6 above, 6 below. They either mean the middle point of the IFLOLS between the 6th and 7th cell, or maybe something else is going on there because of the angle that the IFLOLS physically sits. Could be some other, more intense description that really doesn't matter for our purposes here. All right. The IFLOLS. Using LSO NATOPS figure 3.1 and 4.1 and 4.2, we can extrapolate an effective focal point for the IFLOLS lights. We first have to understand what the IFLOLS is doing. The IFLOLS has 12 cells, the top 10 being amber and the bottom 2 being red. The total vertical coverage, or arc, of all 12 cells is 1.7 degrees. Each amber cell covers 0.13 degrees, and the total coverage for the 2 red cells is 0.4 degrees. So 10 times 0.13 plus 0.4 for the red equals 1.7. Note, again, there's not a physical center cell. Because the total coverage of the 2 red cells is 0.4 and implied 0.2 degrees, the 3.5 degree glide slope exists. All this to say is that a 3.5 degree glide slope exists between the 6th and 7th. Figure 4.1 in that document indicates distance from the IFLOLS in nautical miles when it should say distance from IFLOLS effective focal point. Super minor, but found that. Some of the more mathematically astute may have realized that if you start with the assumption that the 3.5 degree glide slope emits between the 6th and 7th cells 0.85 degrees, that means you have 0.85 degrees up and 0.85 degrees below in order to still be emitting a light from the IFLOLS. You'll notice that if we take 6 cells times 0.13, we end up being short of 0.85 by about half a cell. So where does that remaining 0.07 come from? I don't know. I'm, for the purposes of the game, they may have actually inadvertently, not inadvertently, but maybe misinterpreted or took this kind of literally. I'm still a little confused on this myself, is that if you start from the top and work your way down 0.85 degrees, that means that the 3.5 degree glide slope would emit from about the middle of the 7th cell instead of the middle of the cell assembly, lined up with the horizontal datum lights. That actually makes sense, but just the numbers here don't support it. I would chalk that up to, a lot of times in the LSO NATOPS, they do say these are approximate values, so I'm probably taking some of these values a little too literal rather than just representative of what it should be. So don't dive into that too deep, although it is worthy of discussion to see how DCS interpreted that. All right, the IFLOLS light beam, here we go. It doesn't light up an entire cell like we see in game. We see a thin slit here, and this picture was taken, I assume, from, 20, 30 feet. You can see that man's arm there. He's probably a standard height person. But that horizontal slit actually appears taller in that cell the further out you are. So, in other words, if you are in between cells, it's not like you don't see any light. The beam will emit from both cells, making it appear to be one. They kind of blur together. So that distance, the slit gets narrower the closer in you are, but for the purposes of our discussion relative to the game, just worthy that it doesn't work like effectively the stoplight that we get in game. You're able to, in theory, see more resolution inside of a single 0.13 degree cell than what we are. But it's my understanding that only happens pretty close in. I have no real world experience with that, but that's what the real Hornet drivers seem to imply. Okay, we can determine the effective focal point. Get my notes up here on the other page. All right, sparing you a page or so of geometric proofs, we can establish the relationship between the chord and the IFLOLS, 1/2 H, 1/2 H, right? And the vertical coverage at a distance. Combining this with the data in figure 4.2, we can back into an effective focal point by finding the slant range from that glide slope at the ramp to the focal point, the hypotenuse, right? So, determining the effective IFLOLS focal point. Note that the optical touchdown point is below the deck line by 11.473 feet. When I first started flying, I thought for some crazy reason that it was along the deck line, and I was kind of spotting the deck. You're not supposed to, but I had problems seeing the meatball and all sorts of things, but in VR. But yeah, it's below the deck by 11 feet or so, and it's on a slant range from that 3.5 degree glide slope by 187 feet. So kind of interesting there, though. That is the point that you'll ultimately aim for. That's not the point that your velocity vector is pointed the entire time. That's a different discussion, but that is where your plane should be lined up with and headed the entire time. So this might be a worthy discussion here about hook and eye path sensitivity. So we know that the hook eye value is 16.35, but the parallel path of that is 16.319. Very minimally different, right? But I'll show you why we might care about that in a little bit here. We can go down to and figure out this, what I mean by sensitivity. I've heard it described as you have a certain window that you need to pass through in order to, land. Your eye needs to pass through in order to land on a carrier. And I used to think it was the funnel, as it's kind of described, the funnel of light. And you can see from that table that at no point does it really get narrower than this 2.47 feet. That happens actually beyond the IFLOLS. So that happens closer to the focal point. But I think what they mean is actually this. If you're flying that 3.5 degree glide slope, as long as you're flying that glide slope, you have a window of, you can see there it's 2.47 feet, assuming you just go over the top of the 2-wire in order to hit the 3-wire. I think this is probably another reason why it's not so important which wire you hit, so long as you fly a good glide slope path. Now, there's some things that we can look at in the geometry that indicate that if you fly it safely and don't violate certain rules, you'll never hit a 1-wire. That's kind of part of the reason why the newer ships are 3-wire ships anyway, because you shouldn't really ever hit a 1-wire. All right, now we're going to pause this. And now we've opened up CATIA. What I have here is an imported model from DCS of the Stennis. We can see that the origin begins down here at the intersection of all three of these planes. We can see, if you look at the compass up in here, I'll try to wiggle it so you kind of understand what it's doing, that X forward, positive, is that way, Y is vertical this way, and Z is to the right, positive that way. I've also done the same thing for an F-18, although not the F-18 from game. I've actually got this one from FSX and was able to take apart some of it to figure out the eye point and the hook point. So another thing that I had to do here is determine the deployment angle of this. So I did that basically visually from references as best I could within reason. It's pretty darn close angle-wise. So with that, I've drawn some lines here, and you're probably wondering what those are for. You remember that 16.139, that parallel distance value? Well, we know that's the path it travels down. And I've got a center line here because if you fly Bankler's mission, he actually does all of his measurements to the center line of the jet. So I assume that FSX's center line is the same as DCS's center, not center line, but center of model. It's not really center of gravity, but center of model, which makes sense because I bet you McDonnell Douglas gave him the outside mold line models to work from. So yeah, that's what I've got there. And that actually makes sense because, you know, if you look at your PlatCam guides, that the top of the canopy lines up with those two. So hey, that looks correct, visually correct. Ignore the stab here. That's just artifact from the model import. I think they show it animated in different positions. Nevertheless, we'll jump back into the boat here. What I've got here is that all that NATOPS data that we just looked at. I've basically drawn that out along the deck line. So what I mean by along the deck line is, look at the some default points here. If you open up and explore some of your folders in there, you've got two Lua files, a John C. Stennis Lua and a John C. Stennis runways and routes. And all of those, actually I should say all DCS models are done in meters. So they list some points in there, which you can deduce are points. And if you put those points in-game, or in this, in CAD, relative to that as the center, the same model center that we exported out of the game, then, hey, that lines up. You can actually see Cat 1. Hey, that looks pretty close to Cat 1. Same thing for 2, 3, and so on. They actually also define a touchdown point and a touchdown line. And yes, it's a little off, not by much, but that's the center line lights. That would probably indicate center. But I've done everything to that center line because, hey, that's the way they've determined it, or defined it, I should say. So some people have said that, well, no, the Stennis isn't actually wrong. It's right. Whatever analysis you've done is not really valid. I don't think the data shows that, though. Sorry. If I align the hook touchdown point from the NATOPS data in between the 2 and the 3 wire, none of the other data lines up. So that should be the 4 wire, but we can see that our 4 wire in game doesn't line up with that. That should be the 1 wire, but our 1 wire in game doesn't line up with that. This line right here should be the ramp position, but it's not, and very clearly not. So, you know, just to show you, the hook touchdown point to the ramp should be 230 feet. Oop. Picking point. Not do picking point, so you won't yell at me and claim that I had some sort of inherent error and therefore everything's wrong. Yeah, 230 feet directly on. And we know that this angle here, between that point and that deck line, is 3.5 degrees. So that creates a problem. The ramp should be out here, but it's there. Well, I wonder by how much. I can actually measure that. We'll go from that point, which should be the ramp, to where the ramp is there. I'll just use the lights there, 19 feet. That's not good. I know this to be correct, though, because I know that these two are parallel, because I drew them that way. I know that this represents top of amber to center line, so let's not do picking point. Top of amber to center line, 0.85 degrees. This is the bottom of the red. I know that my hook to ramp clearance is 14.1 feet, 14.067, same we calculated in the presentation. And I know I to hook is 16.35. So all of this lines up our eyeballs and the hook to put us down between 2 and 3. So, and I can even actually go in here and look at this model and say, well, where do you want true to be? What if we line up the 1 wire with the 1 wire in game? You can actually see that's kind of a good indication of just how far off the total spread is. The distance from here to, let me grab a picking point, CAD jargon there, 7 feet. So if I were a little bit more precise with that, I think you'll find the total spread to be short in game about 9 feet. But very clearly off. So why this matters is what I did in my previous attempt at this was I made a incorrect assumption, and looking back on it, it was kind of a silly one to make, is that I assumed that the physical geometry or the physical location of the IFLOLS model in game was related to the apparent beam of light that it was emitting. I should have thought like a programmer and realized that that's not necessarily true. They could have put this wherever they wanted, and in software determined how the lights actually worked. We do know that the lights actually work based off of eye position in game. If you've ever been on the deck of the Stennis and done an outside external view and looked over to the IFLOLS, it's actually and moved your mouse up and down to rotate your view. You can actually see it's related to the eyeball position. So they're actually true there. They've accurately modeled that, which is good. But the position is wrong, but because this whole thing is off by 5% or so. 5% may not sound like a lot, but over these long distances, it is. We can also see from here that if you want to visualize where the focal point is, it's actually like we said, 187 feet past that, along that slant line, past the deck, and about 11 feet, 12 feet below the deck. So, in other words, it would look like, let me exit out of here. It would look, I don't know, roughly like that coming in. Ignore the slant. Let me fix that for you. So yeah, it looks something like that going in. Don't spot the deck though. Don't spot the deck. Fly the ball, and even the DCS ball. And I'll show you why here in a second. But yeah, the Stennis is wrong. So if that's wrong, what does the ball look like? Well, let me highlight in orange what correct looks like. What you see in white there is the same thing, but with some extrapolation of the DCS meatball. So how did we do that? Well, because I know the eye position relative to model center line, I can actually debug the position of the jet. I keep saying center line. I mean center of model. The eye position to center of model. I can debug the center of model position and I make the correction for in X and in Y for the eye position. What do you mean? So basically, we turned on a debugger that was giving us position with really long decimal readouts, X, Y, Z, of the center of the jet relative to the Stennis, the center of the Stennis down here. We taxied, really, starting at the aft, along the center line as slowly as we possibly could. And when a light turned on, we stopped, noted the coordinate, wrote that down, and then kept taxiing forward. And when the next light turned on, we knew that. I could actually show you that here. A little crazy to look at, maybe. But those are all the CGs, and those are all the corrected eye points where the eyeball actually was. Now, yes, that does assume that the plane sits on this plane, which is called the waterline. That may not be true. When it's on the deck, it sits what's called the deck line, obviously. And because of weight on wheels and ordnance it carries and all that other jazz, compression of the undercarriage, it actually maybe doesn't sit like that, but it's pretty close to that, I would argue. So that's what we did. And if you put all these numbers in and project down the angles that those should represent, because remember, the bottom of, as you enter into the bottom of a light bulb, and in other words, they turn on from the bottom to the top, we know the moment that they turn on what that angle should be. You end up with a whole bunch of lines. Let me kind of declutter some of this other stuff for you. Get rid of that. You end up with a whole bunch of lines that you can project down, and they should intersect. Well, I just basically took the average of some points in here and called that the focal point, because obviously we did this experimentally. They're not all going to line up, but they were very, very close, statistically speaking, that is. Nice tight group of data there. So that's our new focal point. That's the top of amber, bottom of amber. That's 3.5 degree glide slope, which does line up internally. If you, like I said, if you pull these Lua files apart, you're going to see indications of 3.5 and a total swing of 1.7. But I mentioned the method that I used here. I was actually either gracious or interpreted the meatball incorrectly, like I did for a little while here. We know intuitively that in order to line up with the datums, perfect glide slope is between the 6th and 7th cell. But if you stare at those numbers hard enough, you'll realize, like I said, that half of a light bulb is missing from somewhere. So if you actually, and that's what I've done here, I actually assume that the 3.5 degree glide slope would be emitting from the middle of the 7th cell. If you do it to between the 6th and 7th cell, it actually pushes your hook point forward of the 3-wire. As in, if you fly it perfectly, you'll never hit a 3-wire. So what else does this mean? Well, if that's the NATOPS and that's the DCS meatball, we can see that, the distance between here I think is like 1.3 feet. This is a little bit more. But we can see that the cone of light that we're traveling down is narrower at any given point relative to the carrier. This is maybe not a big deal. I've thought about why this may be. Maybe, they didn't model the meatball correctly. This is effectively at kind of the deck line. You can see where that point is. Maybe they thought it emitted from the deck and not really below it. But here's a possibility, is that because of the way the lights work in game, maybe it's a limitation of the technology, where they have to basically use a stoplight methodology. They can't show a light within a light, right? That'd be more difficult. Because of that, maybe they wanted to show more fidelity in close, because we know the further out you are on either model, if you're within an amber light, you're within an amber light. You won't be able to tell unless you're close in where that light, the width of that light narrows. So maybe that's what they wanted to show here, is a little bit more resolution in close. But it's not realistic. Maybe I'll use that term. It's authentic in that it shows you deviation, but it shows you too much deviation. That is if you do the numbers and get way too far into it, on the real IFLOLS, you could see any of the top 2 lights and be within that, and you'll miss. You'll go over the top of the 4-wire, assuming, once again, you fly it perfectly. Your plane's set up on speed 8.1. You've nailed that, but you just rode one of the top 2 lights in all the way in. Yeah, you'll go over the top of a 4-wire. At least that's what my analysis says. So it's going to show you more deviation than what it should. So don't let that discourage you. Like if you see your ball starting to climb or fall drastically right as you get over the wires, don't freak out. There's nothing you can do about it anyway, because effectively you're pregnant at the ramp. Whatever energy state you put in there's not much you can do unless you're flying a bit ahead of yourself and maybe making a correction a moment or two before that to set you up to be in the wires correctly. But yeah, there's not much you can do at the ramp. But interesting to note that, we said that this parallel sensitivity, that we got 2.5 feet on parallel 3.5 glide slopes, and everything that I'm shown shows that the DCS meatball is putting you deeper in the wires than it should. And I've been generous here, as I said, with my method. It may even put you over the top of a 3-wire. It's understandably a little bit forgivable. If I was a programmer and was flipping through this NATOPS, and we've always heard you aim for a 3-wire, you aim for a 3-wire. No, you actually aim between the 2 and the 3-wire to yield a 3-wire. You don't aim directly at it, because it doesn't take much to be over the top of it. But anyway, that's that. I thought you might want to visually have a visual representation of what's going on there. That's the NATOPS data. The white is the in-game data, and you can derive what that means for you. But one thing I've done is I've corrected the plat cam in game. It breaks the integrity check, but I've corrected the plat cam in game to this line. I can't deduce where they put their line or their point from. It doesn't line up with even their own runway center line. I don't know if they're trying to be accurate to where the real plat cam is. I have no clue. But what I've done is put mine directly on that center line, looking up at the correct angle. Mind you, they had theirs set at 3.6 for a while. I think the angle went up. So, if you put a crosshair in the middle of the screen, it's already wrong. But I've corrected that, and I've got a little overlay in OBS that I use that shows the meatball kind of superimposed on that vertical crosshair to see where the pilot is. And we've done some tests with that. If you look in my other videos, you'll see Bankler running a test with me where he's riding the top ball, going in and out of that being a Clara ball, and he makes those calls, and it's relatively accurate. So all in all, if you're flying this and you're able to put it down on a 3-wire, you're actually flying a bit tighter than the real one. Not to mention that the wires are closer together, so it's tighter in that respect too. Yeah. So what that means to you, you can deduce whatever you want from that, but here's the real numbers. The Stennis is too small. The meatball is wrong, but hey, it's fun. It's still authentic enough. It's not realistic, because realism concerns itself with facts or reality. Authenticity doesn't concern itself with that. It concerns itself with essential elements. Do we have the essential elements here? I would argue yes. So, if you like that video, give me a thumbs up. I'd appreciate it. Let me know if you enjoy this sort of thing. Thanks for your time.